Aloha.
Hello. Hi. Does this work?
Yeah.
You can hear me. Good. Hi.
Yes. Yeah, so I just made you a co-host so you can share your screen and all that kind of stuff.
Oh yeah, I can do that. Yeah. Let's see if I can share it.
Yeah. How's it going? So where are you right now?
I'm in Manchester.
Okay, that's what I thought, but I wasn't completely certain.
No, yeah. It's good. Yeah, it's interesting to give the talks. I've given a couple of other talks in the US as well earlier, and it's like with the time difference, it's like in that other talk, it was there were people from China, so they had to kind of find some kind of a time slot which kind of fits to everybody.
Yeah.
Yeah. How are things there?
Oh, well, things are good for me. I don't know. Yeah, actually, things have gotten a lot better, as far as the virus and we had a big freeze and all of that goes. Things are improving.
We are still in a lockdown. We can't leave our homes, but kids can go to school finally. So that's the first step, I guess.
Yeah, wow. I can leave my house, but I choose not
to. Yeah. I actually feel like for me, nothing has really changed. Like, except that I give my lectures on Zoom, except on a theater. Mostly I'm working from home anyway. So.
Yeah. Yeah, we usually wait a few minutes for people to join. Yeah, it's actually it's more or less springtime here. We had this huge freeze with I think we had 6 inches of snow overnight, which never happens in Austin. And it stayed around for a week, but after it all melted, it's it was like 80 degrees Fahrenheit, which is very warm.
It kind of reminds me of that one day when I was in Jerusalem, and it was like completely like everything stopped at one day. There was so much snow on one day. It was I felt quite nice because it was like back in Finland or something. But yeah, that was a long time ago, I think.
Yeah, but that's very well. I don't know the weather in Jerusalem very well, but I would not have expected snow.
Yeah.
It seems very unusual.
Yeah, but that's nice.
It's indeed very unusual. Not very unusual in Jerusalem, but we had a huge storm 3 weeks ago. After 6 years of essentially no snow. So
I think it was the snowstorm 6 years ago. That was the one I was in. Yeah.
Oh, that's the one. Yeah, and 6 years ago there was a huge one. As far as I remember, maybe every second year there is a little snow. Something enough for the kids to enjoy, and not too much to disturb their life. Yeah. But 2 weeks ago and 6 years ago, there were really snow, which really stopped the city because, you know, the city doesn't have all the equipment to clean. There is no point.
Yeah.
To acquire this.
I think there was power cuts as well, so there was no electricity and stuff for some time.
Yeah. But it's usually a kind of an holiday, you know.
Yeah.
People, the kids don't go to school, and
Yeah.
well, this year they don't go to school anyway.
Yeah. Yeah.
So you ready to start? You want to get started?
Oh yeah, sure. Yeah. So thanks, Louis, for the invitation. And well, there's a couple of people still coming, but I'll kind of start. So I'll try to keep this a bit more broad with the talk, and it's on a topic which I'm currently just trying to understand myself what is going on. Like this field is just making my head spin all the time. So I've been reading like physics literature for the past months, trying to understand what are we doing, like physically speaking, because I don't have a degree in physics, but I'm kind of curious of what actually is going on with this thing. So I'm learning about this. So, but there is a motivation for this coming from graph theory, which I will also highlight, and then a little bit of this metric spaces, like large metric spaces, like Gromov-Hausdorff convergence. So a little bit go into these topics. And the kind of overview of the talk is I'll introduce a couple of questions from spectral geometry of hyperbolic surfaces that typically people want to study in this kind of context, just very briefly, that you get a heuristic idea at least what's going on. I discuss some analogs in the context of large graphs, especially random graphs. And this kind of touches a little bit random matrix theory, but not much, not just kind of touches that a little bit. And then how these ideas for large graphs, some of these topics that people study, like local convergence, like the Benjamini-Schramm convergence, help to kind of understand some of these spectral geometric properties of large hyperbolic surfaces, actually. So that's what we want to study. And in particular, like, so we will outline some of my joint work with Etienne Lemasson and my student Joe Thomas and our postdoc Cliff Gilmore. Okay, that's kind of the outline. And let me give you the kind of very brief introduction to quantum inequality. If you have ever been to any talks like this by any of the famous people, it's like the same kind of beginning. So, but let's assume that you have a hyperbolic surface. So what I mean by that is like you have the hyperbolic plane, for example, in this case, the disk, and you have a discrete subgroup of this kind of PSL2R, basically 2x2 matrices, and with the determinant identification 1, but a discrete subgroup of that. So then it basically, when you take an element of the discrete subgroup, you get this. You're going to identify them with some geodesics on the hyperbolic plane, and then by choosing suitable generators, you can create this kind of picture, like I don't know what this is called in English. I'm sorry, what is this? It's a
polygon.
Like polygon, yeah, hyperbolic polygon. And then identifying these edges, you get a surface constant negative curvature -1. That's the setting. The reason this is studied is because physicists are interested of like modeling quantum mechanics for chaotic systems. So this could be considered a one-body system of a particle traveling through the hyperbolic surface along the geodesic motion. And that geodesic motion is given by the usual geodesics, like that you have by the parallel transport that you define on the surface. But that's just on the hyperbolic plane, you use the geodesics. And the quantum mechanical model for that is that you want to replace the particle by a wave function that evolves through the space along according to something called Schrodinger's equation. And the Schrödinger equation is defined by usually a quantum Hamiltonian, which is in this case the Laplacian operator. And the spectral statistics of the Laplacian then is relevant to understanding like some questions, which I formalize in a second, what could be the topic. So in any case, there's the Laplacian operator on the surface. you can just define the hyperbolic plus Laplacian operator on the hyperbolic plane, and then kind of lift it to the surface using the group that you get the definition of the Laplacian. There are other ways to define it as well, but that's it's a differential operator, and then we have the spectrum, and then we have the eigenfunctions, which are definitely not always unique. So given eigenvalue would have several eigenfunctions associated to like a basis of them. So we choose a basis, and then the physical observations. This is kind of like there was this paper of Aurich and Steiner where they kind of, it's actually very interesting how they do it numerically. They choose these kind of these polygons, hyperbolic polygons, and with some approximation techniques, they're able to actually draw these functions in some cases. So they can actually go quite high energy, and they see that these kind of pictures for the eigenfunction square. So they see this kind of like a property that these functions seem to spread out in the space quite a bit, and that should be the manifestation of the quantum ergodicity or quantum unique ergodicity kind of in this setting, where the basic idea is that, let me formalize it actually, then you see the kind of more what I mean. So the same setting, but then these conjectures formalize it. So for the mathematicians in the audience, here's what I was trying to say, that you want this, that if you test these eigenfunctions squared on a compact test, like let's say in this case as a continuous test function, you should converge to the uniform mass, for example, along the whole sequence, no matter what basis you choose. There's also delocalization possibility where you could have that they don't get too high values when the eigenvalue goes to infinity. These are very difficult conjectures, right? Even like this second one, for example, I think in some cases it implies the Lindelof hypothesis in an arithmetic surfaces. So I definitely I'm not claiming I can say anything about these conjectures in this talk, and but there are some things that these two relate to. And the motivation from physics a little bit come from the fact that if you think about the hyperbolic surface, you have the Liouville measure as the unique ergodic, like a maximal entropy measure, absolutely continuous measure for the system. And when you go to a quantum mechanical version of this system, the eigenfunctions, the Laplacian squared, are invariant under this kind of Schrödinger evolution, which comes from the quantum mechanical equivalence of the geodesic flow. And then if you go to high energies, lambda is very large, then you can expect this Schrödinger operator, this evolution, to behave a bit like the ergodic geodesic flow. So if the high energy, you kind of expect the invariant states would be basically uniform. That's how I see at the moment, and I'm trying to see it a bit better. But the questions are there like examples that satisfy these conjectures? Could you construct a random model that satisfies these conjectures? Like that's always the hopeful thing, that if you don't know how to prove it, then try to find a set of positive probability that you could find an example. Okay, and that's kind of the goal. And this has been done. This is like in the random graph situation. This is like where I'm going soon. This kind of has been done in that situation. This is a big kind of long-standing field of a lot of people have been working on this. And so I'll go into a little bit that some of this can be done actually. But then you have to be careful what do you mean by the quantum unique ergodicity, for example. That's it. Are there any questions before I go to the next thing? Okay. Large graphs. So this is I tried to find some pictures of examples of large graphs, not just like definition, but you can think about that. Okay, there is like a lot of structure within these things, but then if the kind of questions I'd like to study, like you could ask these kind of similar questions as I mentioned about the quantum unique ergodicity, delocalization of eigenvector, eigenfunctions in this kind of context. And when it's a large graph, maybe possibly a random graph, there's actually quite a lot of things you can do for similar analogous problems in these kind of situations. And then the purpose of this talk, or what we have done, is to translate some of these ideas from these large graphs into the setting of large like surfaces. So so what we start from here, I'm giving you a result that has been done by other people, and to give you like a motivation what we could maybe do. So we have a regular graph, so deregular graph. So you can define one version of the definition of the Laplacian here would be, for example, this adjacency. You have this sum of the adjacent elements of this point x, and then you divide by the degree, and you subtract the value of the function at this point. Okay, and then you have one version of probability model, uniform probability, that gives you the sampling uniformly from the space of our deregular graphs. So fix the degree, and n is the number of vertices you fix, you get this bundle. And then you define the set of all L2 normalized eigenfunctions. That's like just all of them, no matter what's the eigenvalues, that's all possible functions that you have. Then in this situation, if you take a random regular graph, I'm just choosing a more simplified version of the theorem. So it's not exactly what how they stated it, but this is what is implied by their work. This is one of the versions. There are other papers as well around this by other people as well, and also from random matrix theory. But the basic idea is that you have this kind of really strong delocalization property. So it actually, in some sense, this is the best that you could hope, because the most uniform vector on the graph, well, this is a eigenfunction, would correspond to a vector. It's a vector is basically a matrix. You could think about the Laplacian. Then it's 1 over the square root of n is the kind of when you put uniform weights in terms of the L2 norm, that you would have then L2 norm being equal to 1. And the L infinity norm then of course is 1 over square root of n. So this is kind of saying there's some fluctuation, log n squared, there's some fluctuation coming from the methods, and which you kind of expect probably when n goes to infinity, that the domination comes from the polynomial error. And you can see it's a probabilistic estimate with the degree condition, that you assume the degree is growing, albeit quite slowly, but it's still growing. I'll come to this degree stuff later. This is something I really don't understand what's going on. This is something I need to really, maybe some people in the audience might know. I'll ask you the question, what is going on here? This comes to when I go to the surfaces, this degree thing. Okay, so that's what they proved. There are other statements as well, but do you have any questions before I go to what we have done? And how this relates to Benjamini-Schramm convergence and all other stuff.
Are there any results where the degree is fixed? I mean, maybe you get worse bounds or something like this.
Yeah, that's a good point, actually. I haven't thought about that. Does anyone know, actually, is the other papers? The only papers I've seen, there's always a degree condition, it's growing. I'll come back to the degree condition because it's kind of related to in the spectral side when I go to the surfaces with the eigenvalue, actually, which I kind of conjecture that you might have to assume something about the degree always, but okay.
Okay.
What's kind of driving this is let's define Benjamini-Schramm convergence. So a sequence of graphs, Benjamini-Schramm converges to a tree. In this case, well, for example, you could think about this could be deregular graphs, and then they converge to deregular tree, for example. If you have this kind of set where you take I think it's sometimes called the thin part, but it's basically the set of points where you take locally, it looks like a tree. So it is you like cut a piece of the graph and it looks exactly, it's a tree. So it doesn't have short loops, loops at all in this sense. So you have basically a tree, and you define this set of points where it kind of doesn't look like that, but it's just like when the R is, for example, fixed, it disappears, then that proportion of points disappears with this set. This is one of the things that is driving this because, again, if this is the wrong reference, please shout immediately, but I wrote it in this form because there's a theorem like this for random surfaces later on, what I will talk about. But if you have deregular graphs and you set all the graphs that have n vertices, then, for example, there is a delta independent of n, such that if you take the thin part with this kind of logarithmic growth, with d, this is a D-based logarithm. This is basically kind of saying quantitatively that you Benjamin-Schramm converge to the tree, kind of in this kind of probabilistically, that this probability converges to 1 when n goes to infinity. And there's also, of course, the uniform spectral gap, like there is a beta. Here it might be positive or negative, depends on which sign I put the Laplacian. Do I put the, do I define the eigenvalues with minus lambda or plus lambda in front? So, but basically there's universal spectral gap that it's concentrated on this interval outside the, there's this beta that kind of, you're always staying within this range. So it's like an expander family in this sense. So this is kind of what you expect to see from the random graph. So that's kind of the geometry of them, kind of what they should look like typically, asymptotically at least, when the number of vertices goes to infinity. And this is kind of one of the things that drives the theory, actually. When you go into the proofs of this quantum periodicity at some point, there are ways to like use these ideas in some situations, like Volcker tree approximations that help the theory. And this is the same in our case. When we do this stuff on surfaces, we have to replace somehow this Benjamini-Schramm converges to a tree to a Benjamini-Schramm converges to a hyperbolic plane, actually, in our case, for example. I'll come to this later. And the spectral gap condition is kind of the same. It's like you just assume that there's a uniform spectral gap from below. It depends on the random surface model, what kind of a gap, the uniform spectral gap you get. So the kind of equivalences. So what we see, like vaguely speaking, the large cardinalities would correspond to large area or large genus of the surface. And then when you say locally a tree, like this Benjamini-Schramm converge, it's like exists locally an isometric piece of the hyperbolic plane. I should say maybe isometric piece of the hyperbolic, but it's really, there's in a big ball, it looks exactly isometrically like a hyperbolic plane. In our theory, we always use these heuristics when we try to get ideas from the graph situation to the surfaces. We always like take this approach to make something happen, especially when you do the spectral theory of the Laplacian. We are trying to keep this in mind. And then this has been done a little bit, like people have done kind of delocalization in the surfaces in this way. That there was, for example, this is really goes to the number theory side of this whole field. So for example, Abhishek Shah has this paper where he studies these congruous covers of the modular surface. And these Benjamini-Schramm converge to the hyperbolic plane when the level n goes to infinity, which is basically the same as the area goes to infinity or the genus goes to infinity. It's all the same actually in this situation. If you would have this kind of the same situation, and they get this, it looks very similar to the result by Bauer, Schmidt, Knowles, and Yao, but it's now for arithmetic surface. It's not a random surface, a fixed arithmetic surface. And okay, they don't get the kind of the optimal exponent. They just get this x to the power minus 1 over 12. And that comes from the kind of fact that they are using this special basis of something called Hecke basis of the eigenfunctions of the Laplacian, which have certain extra symmetric structure. And this symmetric structure can then be used in the proofs using something called an amplification method, which is a typical method to bound L infinity norms, for example, of eigenfunctions. This goes back to the works of Iwaniec and Sarnak, actually, how they approach this. And the way we can actually go further with this is kind of the connection we always use, is that when you have a regular graph, for example, or any graph actually, you can kind of identify it to a surface, like just a topological surface, by gluing handle bodies along the surface. So you can kind of take this graph and then start taking these like geodesic loops around these edges and glue these like pans, for example. In this case would be pairs of pans, but in general it could be handle bodies. It could be more topological, more shapes. This is like, if it's a D-regular graph, you would glue like D handle bodies. So a handle body would be like, this has like D tentacles coming out of it or something like that. And you glue them. But then the problem is that, okay, these are nice topological surfaces, but could you create like random surfaces, like somehow like randomize the Riemannian metric, for example, to make it somehow more useful to study, let's say, the spectral theory or something? And how does it connect to here? Like if you have a random graph, does it somehow help with the other side or vice versa? And sometimes it does and sometimes it doesn't. So that's what we've noticed now. So the model we use, this is a model, Weil-Petersen model, which is kind of done with this kind of gluing stuff. So I'll give you a very heuristic way how you create this random model of surfaces, just with a couple of pictures, if you haven't seen this before. So we fix a compact Riemannian surface of genus G, anything, just whatever is like something, it has some metric, but it doesn't really matter what it is initially. But from this XG, we can create new surfaces with the following procedure. What we first do is that we find some geodesics in the surface, like there's actually a certain number of geodesics, which we cut along the surface to create these kind of pairs of pans. So any surface of genus G, you can cut into these components where you have like pairs of pans with these three boundary geodesics that you do, if you have genus G. This is called the pairs of pan decomposition of your surface. This is one way you can always do this for these surfaces and create these kind of pans. And then you can re-glue them back in. But now, because the Riemannian surface, it has some metric, so you can change it. You can kind of change the metric that actually say that this geodesic length is bigger now. Let's make it bigger, and then glue it back with a twist. So we twist it slightly and then glue them back together. It's the same way. So we glue them back on the same along the same geodesic. We don't like alter the order. We don't switch them around or anything. We just glue them back in. You just created a new metric to the Riemannian surface by using this operation. This Riemannian metric allows you to do a lot of kind of things. So actually, there's some further identification which allows you to create a space of metrics. This is the moduli space of Riemannian surfaces that comes out. But then the basic model is that you just put a Lebesgue measure on these lengths of the geodesics and Lebesgue measure on the twists. You get 6G minus 2, is this, if I counted correctly, dimensional Lebesgue measure basically. And that's kind of been lifted to along this identification, this topological identification into the space to create these nodes of random surfaces. And it actually creates a set of random hyperbolic metrics, actually. This is the kind of theory that comes with when you have a genus bigger than 2, that at least 2, then you get actually hyperbolic structures from here. So these, you can think about that actually these are random hyperbolic surfaces. They end up being what this model gives you, like what comes up. And what is known about this, these are the recent theorems, like Brooks. Well, okay, this is a different model. Brooks-Macover had this earlier model where there's, well, actually, I don't know if earlier, like maybe later model, but depends on. But this is a more like combinatorial model that they studied the bottom of the spectrum, that there is some kind of a spectral gap, uniform spectral gap for the bottom of the spectrum. That's Brooks-Macover. They have this random triangularization model of their surfaces. And then this Weil-Petersen model, this was Mirzakhani. I think probably she was the first one who proved that there is some, okay, this looks kind of crazy. This is log 2 pi plus log 2, and then this times 1/4. This converges to 1. And this was actually improved recently to 3/16 by Wu and Xu. This was just a recent preprint on arXiv, which was actually some of the ideas that in this paper of Wu and Xu were based on this slightly earlier paper by Magi, Naudam, Kuder. But they studied another type of a random surface model called a random covering model, where they fix a base surface Y and then start to study its random covers, which makes it the genus to grow. And in that model, they proved this 3/16 as well. But anyway, there are so many models. There are various models of random surfaces. The one we are using is the Weil-Petersen one. Because of some results of Mirzakhani, she had like really nice integration theorems that she developed for those, and we want to use those same theorems. Actually, we did use them to make something happen. So, but there's a conjecture here. This is I think Andrew Alex Bright maybe mentioned this in a survey that it's actually 1/4. This is like coming from the Selberg, in the arithmetic surfaces. It's kind of the same, motivated by this same conjecture in this situation. So that's what is expected.
There was a recent talk by Alex Wright. So Alex and another, his co-author, I don't remember, Lipnowski. So they have another proof of the Wu, of the same theorem by Wu and Xu, yeah.
Oh, yeah, yeah. And also I've heard...
I just wrote that in the chat as you were saying it, Lewis.
Yeah, so they have an independent...
It's redundant.
Yeah.
There was also like, I don't know if you saw a preprint by Nalini Anantharaman and Laura Monk. And they had some like Weil-Petersen bound, but in the preprint they say they are currently working on trying to prove this 1/4 thing for the Weil-Petersen model. So in the preprint it says there's a comment that this preprint is kind of related to that. So I don't know, maybe something will happen. This 1/4. That would be very interesting if someone is able to do this. Beyond the 3/16, but there's some real actually there's a reason for the 3/16 in the proof. So I'm not sure how you overcome this with such a probabilistic method.
I'm curious, is this 3/16 the same 3/16 that appears in Selberg's theorem?
Yeah, I've seen this there as well. Yeah. Well, but it comes. Yeah. Anyway, it comes from the use of the trace formula. I've seen that they use with certain test function. That then with this nice test function, the 360 comma is the natural comes out from that. And in the random model, you just need to study their short geodesic loops of to be able to control the trace formula. Then to be able to make some sense out of it. That's also the idea. Okay, so let me go to the high frequency. This is what we, the quantum unique ergodicity on that stuff. That's the high frequency spectrum. So, okay, so we have this, again, the same setting. We have compact hyperbolic surface and we have the eigenvalues. So there's a spectral gap because it's a hyperbolic surface. So lambda 1x is positive then. And then there's an orthonormal basis that's just fixed on basis. And what we proved is, this is actually a combination of a couple of works, but we proved this kind of like, not a quantum unique ergodicity, that would be insane. No, never, but this is something that the best we could do is that we get this like quantum ergodicity, which is weaker than quantum unique ergodicity because we have to average over a window of energies. So we fix this window I. It's like a window of energies of the quantum system, compact interval, and then we take a random surface in the moduli space, and then the probability that for any L infinity function in the surface we have this bound. This converges to 1 as the genus goes to infinity. So you have the L infinity norm appearing here as well, like that's the control. But you can see that this is like, without this averaging, we are basically averaging over the spectrum and these eigenvalues. This would be the quantum unique ergodicity statement, but not in the same way because you're actually taking the genus to infinity. So you're fixing kind of the spectrum. So you're fixing the energy. So in the quantum unique ergodicity, you would move, the interval would be maybe from 0, maybe 1/4 to lambda, where lambda would go to infinity. So it would be moving interval to infinity or something like this. Here we fix this interval, but this is only the beginning. We are like currently trying to do this kind of hybrid theory where you would have both statements going on. That's one of the theorems. And then for the delocalization, which kind of relates to Bauer-Schmidt-Knowles-Yau, we proved this, that you have this delocalization, but shamefully, this is only for logarithmic rate with this. So if we take any eigenvalue lambda j bigger than 1/4, then for any epsilon, you have this kind of like statement that for any, you can see that this L infinity norm of the eigenfunction, the Laplacian, is at most logarithm of the x. So remember, if you compare to the arithmetic surfaces, you have the actually the volume without the logarithm, but then it was with -1/12. But then for the Bauer-Schmidt-Knowles-Yau, they had actually the degree square root of the number of vertices So the expectation, what we expect actually, this is what we would expect it to be. It should be without a logarithm. And why I think we can maybe prove this, why I think this might be possible. We didn't use in this paper any ideas from the Bauer-Smith-Knows-Yao. We didn't actually take full advantage of their ideas to make this happen. We just use kind of I think what we did in this paper, for example, we used we kind of used just the basic propagation method until the C log genus or something like this, which kind of is like we used the local tree approximation, Benjamini-Schramm convergence a little bit like that, and we go into this scale. And then we just use Mirzakhani's integration formula to get that, okay, we kind of have enough at this scale. But because we only go that, we don't go too far, we don't get enough decay. It's kind of like the kind of naive argument, you would say, like the kind of thing that you do with the trace formula. The first thing, this is the best kind of what you can get. But I think now we're trying to push this further into getting actually how far can you push this method to maybe get this without the logarithm. But then notice that this is also a horrible estimate in terms of the eigenvalue. So for the eigenvalue, if we would have eigenvalue here, it would be e to the power eigenvalue. It's like you don't want anything like that. That would be horrible. The reason for that is this trade-off, which is called Heisenberg uncertainty principle. If you want to localize spectrally in the spectral side of your argument, the trade-off is that your geometric side gets horrible. And then the other way around, if you want to do something better in the geometric side, what we are doing with the genus thing here, then you have horrible estimates on the spectral side. So there's like this balance of like which one are you using? Do you want more better estimates of when the genus goes to infinity or the volume goes to infinity, or do you want better estimates when the eigenvalue goes to infinity? Usually when you want the eigenvalue to go to infinity, you also take an advantage of the interferences that come from the when you propagate quite far. So then you can use the mixing of the geodesic flow, for example, in some of these statements. So to get some improvements over this, like for example, in the in like this theorem, if you prove this quantum ergodicity in the when the eigenvalue goes to infinity, you actually end up using a lot of the geodesic flow on the surface, the chaotic properties of the flow to make that happen. We don't use that. We don't need that in here because we don't propagate so far as we would actually end up using that statement. But the kind of the way the Benjamini-Schramm convergence appears with this whole discussion is, let me show you kind of how. So these couple of next slides should highlight you how the Benjamini-Schramm convergence in the surface situation kind of appears. So, so I want to give you an idea now how to prove, let's say, this statement, that what are the things that go into it. And the first thing that you need is we have the settings, and then we use this injective radius of an hyperbolic surface. So what is injective radius? So it's basically the largest ball that you can fit inside the surface, which is isometric to a ball in the hyperbolic plane. So think about like in the case of in the graph, it would be the largest ball you can fit inside the graph, which is it is a 3. So this is the analog of that. And then we proved this kind of quantitative statement earlier. And okay, this looks a bit messy, but it's basically that we take test functions which are average 0. It kind of is fine to just consider those average 0 test functions. But now you can see that this thin part appears here. And there's appears the spectral gap as well. And there's the volume of the area of the surface and the injectivity radius. Everything appears here. It's so quantitative with geometric estimate. And the way we got this estimate was combining some this kind of harmonic analytic ergodic theorem by Amos-Nevo, where he proved this kind of like well, if you take like a set on a lattice that is defined by like lattice elements with a spectral gap, it doesn't matter what the set looks like. It could be like an open set or some crazy looking, as long as it's a positive volume and you average over this set, then that you have like exponential decay for this. And this follows from this method called Kunze-Stein phenomenon, which allows you to get this sort of an estimate. And this is like in the proof of this estimate. So we just plug that estimate in. We have to do some reformulation to be able to get it into this form. But it's basically then comes out of this way. And then this thin part appears because at some point where we go from the surface into the plane, so we are kind of like moving back and forth between plane and the surface. At some point, you end up to this kind of there's some propagator that we are using at one point, and this kind of propagator that allows us to use the Amos-Neville's theorem actually asks how many elements there are in kind of some sum of over short loops, for example. So this becomes a lattice counting argument, and in the lattice counting argument, this thin part actually starts to appear, that if you're below the injective radius, you're fine, and if you're not, so we try to kind of put everything into that low injective radius case. So that's in a 1 minute line idea of that proof of that statement. But I highly recommend to just have a look at the article to have a see how this actually is done, and I can explain a bit more later as well. But in any case, you can see that there is this statement, and now the question is, so what if you do this for a random surface? So the Benjamini-Schramm convergence of hyperbolic surfaces means this, that it's like this in the graph. So you have this sequence of hyperbolic surfaces, and the thin part converges. And the heuristics is that the Weyl-Peterson random surfaces of genus G asymptotically Benjamini-Schramm converge to the hyperbolic plane. It's a very similar statement as in this case of graphs for the uniformly sampled graphs. So this is exactly the same definition as we had before. So now you replace the tree by the hyperbolic plane. And this indeed is possible. So this was proved by Maria Mirzakhani, and then Laura Monk extended this to the case. She made it better, like more quantitative, actually, the probabilistic estimate. So, but Mirzakhani already considered this case in her paper, and it's like the estimate we had for the graph. So it means that if I quantitatively, when the genus grows, you can take this thin part larger and larger. You kind of quantitatively Benjamini-Schramm converge the hyperbolic plane. So it's like in the graph case. There's, of course, the uniform spectral gap. As I said, this is improved already to 3/16. So actually, when I was preparing this talk, I gave a similar talk a long time ago, and that result wasn't available then. So that's why I'm using this. I could have replaced this with 3/16. So, but at least this is enough for us. We don't need the 3/16 because we just need, there's a lower bound. So that's all. And then that's then the other thing that you need from this other thing, that this set AG that satisfies these properties also has this Y law going on. So this was Laura Monk proved this, and this is kind of follows from the Selberg-Trace formula, but you need to do some more some balancing act with the definitions. But basically it's saying that the number of eigenvalues in this interval, this spectral window, is roughly the volume of the surface. And then there's some error terms that decay in the genus, so they kind of disappear in the estimates. The reason you need this estimate, this Y law, and this one, if you combine these two, so this is actually the same set AG. In this AG, you have this estimate. Notice you need this all these injected radius bound from Ibolo and this to make this happen, and the Benjamini-Schramm estimate. Together, you have this convergence, because now you then get this, because if you look at this statement, so this is again the same slide as earlier, that if you divide this by the number of eigenvalues and you sum, and this start to behave like the volume, then if you look at the quantitative estimates I had below earlier, if you divide that by the volume on both sides, you get this logarithmic decay in genus. So let me show you this estimate again. So can you see this? If you divide by the volume both sides, you take out the volume term from here, and then you get the thin part, and the Benjamini-Schramm convergence allows you to get that also disappearing, and then you choose the logarithm of the genus with the R to make this like decay in that. That's the idea of the quantum ergodicity. This is kind of analog of the what you would have in the large eigenvalue, but we use it for the large genus limit that you get in here. And then for the L-infinity norms, I can give you the same kind of geometric bound. So we use these kind of loop counting parameters. So if you have a surface X, let's define this parameter Rx and Cx to be just some parameters that for any delta, the number of primitive geodesic loops of length r passing through a point is at most sub-exponential in this way. That's a constant and e to the power delta r. This is just a definition. So it's nothing to, it's just saying that for a surface, and you can always notice that this always is true with where Rx is injectivity radius and Cx is 1. This statement is always true, of course, because the injectivity radius is kind of the upper bound that if you choose the injectivity radius bigger. But the problem is that this is actually, if you can improve it even a little, you can get something in the spectral side of the eigenfunction. So this is what we can get. So that's a kind of statement. It's just purely geometric. And you get an L-infinity norm bound for the eigenfunctions in terms of this constant that is here in front, and then this Rx. So the proof of this is taking a propagator, and Shimon Brooks and Elo Lindenstrauss used in their earlier paper where they studied the quantum unique ergodicity in the because they wanted to get this like joint quasimodes quantum unique ergodicity theorem, and in that paper they studied this kind of like one kind of a propagator that was like a cosine kernel, which they cut the high frequencies out. They modified it to cut the high frequencies out, which was horrible for the eigenvalue aspect, of course, but we don't care about that. So we use that propagator here and plug it into the kind of plug into the Selber trace formula and try to make this like happen. Then you get this out as the statement. The geometric side kind of translates into this this condition. This comes from the trace formula, because in the trace formula you have the loops coming in out, which I can show you in a bit. And then this everything follows, where if you choose the Rx to be not injectivity radius but C log X. Okay, you have to choose the Cx to be injectivity radius x to the power -1 actually in this case. But in order to then prove this, we need to basically prove that the random surfaces you can do this. That's something that we needed to use the Mirza-Kani's theory to be able to make this happen. So we need to prove this statement that this actually holds in this sense. That's usually the idea with how you get into this setting. Okay, so that's the basic idea, and then the conjecture, what I would hope to prove, or this would be interesting to see, that remove the logarithm. So that would really go into taking out more of the random graph ideas and kind of see what's actually happening. As we compare these kind of statements, I would expect something like this would be true. What this would imply, notice that this again, this is depending on the eigenvalue. But what I would hope that if one could come up maybe a propagator that could kind of not localize too much on anywhere. It's like, because the problem is that if you want to do a good geometric bound like this, it might be very difficult to apply the eigenvalues. So you might need to use semi-classical analysis to take advantage of the large eigenvalue side, maybe apply some of the ideas from the it's kind of quantum chaos community with the propagator beyond towards the lambda, for example, which allows you to use the mixing the geodesic flow maybe. So that could be a hybrid bound actually here. That would have both of the large eigenvalue and large genus at the same time happening. But that might be this might be the first step to actually prove something like this. In terms of the original conjectures, with what Peter and Zev and the other people and Henrik asked, this is not giving anything towards them. What it gives you is this kind of like, it's like there's this thing, there's all these papers on random graphs which say that this is a quantum unique ergodicity statement. We prove eigenvector delocalization. And these ideas are based on random matrices, that random matrices have eigenvector delocalization, for example, on certain, if you assume certain properties on the matrices that they come from certain ensemble, for example. And what this is like doing, what we are taking is those ideas from those setting and trying to get them to the surfaces, the deterministic setting in some sense. So what we are basically studying is like the random Laplacian, that the Laplacian is the matrix, the random matrix that you would consider, and the parameter that is changing in the set of random matrices, you have the size of the matrix, for example, gets bigger, and then you have some statistical properties of that matrix. Here it would be the genus is making it bigger somehow. And then you can say something about the statistical properties, the eigenvectors of this Laplacian. So it's kind of like, if you don't know how to, I don't know, was it, when I was in Jerusalem, I think it was Shahar and Shela who told me that if your method doesn't solve the problem, change the problem. It's like, so just, okay, this is a different problem. So at least it seems to give something out. So that's the main thing. I'm not sure how much time do I have left. I have some things on the ideas of the proof, but I'm not sure if it's, if you want to see a slide or not. It's up to you. Like,
I think it's good to see a slide or two.
Okay. Yeah.
Yeah, I mean, it's probably good to leave a few minutes for questions. So maybe, let's say you have 7 minutes, just to.
Okay. Yeah.
Yeah.
That's actually good because I can give you like the easier proof, which shows you the main idea of the L infinity non-bound, which shows you kind of how the trace formula appears, and which kind of reveals a little bit how the Benjamini-Schramm, the thin part, comes out a little bit. So just this estimate. This is actually not good enough estimate to get anything in the large genus limit, because actually Mirzakhani proved that the expectation of the injective radius is bounded when the genus goes to infinity. It doesn't grow, it actually stays bounded. So you can't use this to get anything like interesting. It's just bounded by a constant times the L2 norm. But anyway, it kind of gives you an idea that if you would have a sequence of surfaces where the injective radius grows to infinity, then you could get something. Like then this would give you a decay of this time. But let's take an L2 normalized, and I use this kind of notation. I use lambda squared to make this happen. And then what I do is that I choose R to be the injectivity radius of X, and I kind of define this kind of a localization with height R. So it is basically a function, bump function that is localizing, and it has a height given by the injectivity radius, basically. And what I do is that I want to define this test function rapidly decaying, that the support of the Fourier transform is inside a compact interval, which basically means that if you take then this function xr at 0, then it's roughly at roughly r, because it's the integral is equal to 1. That's the kind of setting you want to use the trace formula. So let's use the cellular pre-trace formula actually, because then we can take pointwise estimates. And the pre-trace formula, I'm using this as the test function. I'm taking this characteristic function, which localizes around this lambda, like here. So it's kind of putting all the mass around this point. So I'm doing like, but the height is given by the injective radius. And then the right-hand side, I kind of put this kind of Fourier transform of this in some sense. This, but in this, because of the properties of this function, it can actually be written in this form. But you can think about it as some kind of a kernel that comes out of this characteristic function, and then you have this like leading term side here, which you have in this setting. So that's kind of just plugging this into the trace formula directly and getting this kind of expression. Why is this useful? Is because now you can just see that because the support of this kernel actually turns out to be inside this XR, it was because of the support of the Fourier transform. This thing was inside here, because this is kind of like a Fourier transform, then you can actually get this bound. And because R is the injectivity radius, and this is summing over the group elements, which are not identity, then if you take a group element, it would push your point outside the thing. So if you are less than an injectivity radius, then you don't have this element. So you can kind of like throw away this whole sum, because the distance would be like too large, you know, like it's the kernel is supported on a small smaller set. And that allows you to then estimate this, because then you're just left with this final term. And then you can divide by the injective radius, and this was always a squared here, so that gives you the square root. This is just in the case of the injective radius, and this doesn't work if you want to get what we wanted, so you have to use a different propagator, which is the one that Brooks and Lindenstrauss used, but then which makes it more crazier, but then it's still kind of the same idea as this, so it's not too different. The problem with that propagator is that then you can't really throw away this sum, because you're left with those terms, so you have to control them a little bit to make them happen. Okay, that's kind of the idea, and then the way you can then do that. Okay, this was what I already said. Is you replace this cosine part with something which is a bit more cutting the high frequencies, and then it's possible to do that. But and then the geometric side, this is something that I have a few minutes left, so this might be the more interesting. So how do you prove the geometric side of this whole statement? So what I mean by the geometric side of the L infinity norm is a statement that it's like this, that you don't have to use the injective radius, but you can use c times log g instead. And the way you can do this is then we are basically proving that this counting parameter, remember that I bounded the L infinity norm from above by the square root of the constant x divided by the Rx, this counting parameter. So if I can prove somehow a bound for that is Rx can be chosen to be equal to C log G, then I'm done. So that's what I'm doing here, C log G is inside here. And then to prove something like this, that this decays, this is like the complementary then for the thing. So I'm actually proving that there's only one, that it's bounded by one, not just sub-exponential. So just to very briefly remind you before I go into the, where was the sub-exponent? So here. So this actually, NRX, this is what I'm bounding here, is less than one. So I assume that it's not less than one, it's bigger than at least two. So that's the complementary event that I'm now bounding with this thing. And then the way you can bound that is, okay, there is a way to like create subsurfaces from this this set. So if you have this X surface and there exist two short geodesic loop of length at most C log G inside the surface, that satisfies the condition. So there exists an X and two primitive geodesic loops that have this property passing through the same point. Let's assume that they are simple, so that they don't too much go crazy. The picture would be impossible to draw without that assumption. But in that assumption, basically here are the two loops, alpha and beta. There are two possibilities. And then you can draw these triangles, so they kind of pass at some point. And then you take a regular neighborhood of these, and you create a surface, a subsurface of the original surface, and you can cut that out. And then the question of this probability event that I want to bound boils down to asking whether this subsurface exists. So they're kind of equivalent. You can prove that this basically the existence of these loops is equivalent to existence of such subsurface inside the surface. And the way you can prove that is using Markov inequality, that we have something that this fx here is big. Does there exist a subsurface or not? If it's like an indicator function, it's bigger than one or something, and then you get this estimate, and it reduces to an integration of a test function whether something exists. And okay, there's some moduli space notation which I don't want to use, but okay, that's kind of the final slide I want to mention, the integration formula, which allows you to actually then bound those estimates. But this is, I'm run out of time now to get more. I just want to leave the slide if someone wants to read this final statement. So that's all I wanted to say. Thanks a lot.
So let's thank Tuomas.